common issue in modern electronics is picking up an electronic device that you've barely used only to find that the battery is nearly or completely dead. If your device was just on standby or sleep mode, this may have happened because of a small but crucial specification, quiescent current. In today's video, we will explore what exactly quiescent current is and how it may affect your LDO and your electronics. Let's begin. Quiescent is defined as a state or period of inactivity or dormancy. Thus, quiescent current, or IQ, is the current drawn by a system in standby mode with light or no load. Quiescent current is commonly confused with shutdown current, which is the current drawn when a device is turned off but the battery is still connected to the system. Nevertheless, both specifications are important in any battery application. Now that we know what IQ is, we can delve a little deeper on how it actually affects an LDO. The first thing that should be considered is how much power is being dissipated through the LDO when the device is active and how much power is being dissipated when the LDO is in standby mode. The equation below is the power dissipation equation for an LDO. The total dissipated power is equal to the input voltage minus the output voltage multiplied by the output current, plus the input voltage multiplied by the quiescent current. Now that we have the power dissipation equation of an LDO, let's use an example to see how it may affect an application. For this example, we'll be using a 4.2 volt input from a battery that will be regulating 1.8 volt of 200 milliamps of output current and 50 microamps of quiescent current. If you plug those numbers into the equation, we get this, and a total power dissipation of 480.21 milliwatts. Now this is when the device is active. What happens when the application switches to standby mode, where quiescent current plays a much greater role in power dissipation? Let us say that the output current while in standby mode is 100 microamps. The dissipated power becomes 0.45 milliwatts. In this example, quiescent current contributes to nearly 50% of the power dissipated. Now, you're probably thinking, well, that's not that much power being wasted. But what about applications that spend a majority of their time in standby or shutdown mode? Applications such as smartwatches, fitness trackers, and other types of wearable electronics frequently spend their time in either of those states. This means that the IQ of the LDO used for regulation will play a significant role in battery life. Something else to consider is also the size of the LDO. We've come a long way from having these huge linear regulators from 60 years ago to these ultra small wafer chip scale packages. We can see that this also matches the continuing trend in electronics of smaller and lighter products. This is because in these consumer products, the battery is usually the largest and heaviest part of the design. However, designers don't want to typically shrink the battery because that would decrease both the capacity and lifetime of the battery. Therefore, it's critical to keep all other onboard devices as small as possible while maintaining performance. TI has LDOs with peak power performance and a small size because thermals aren't a huge issue for low power dissipation. The TBS7805 is a prime example. It boasts a 0.65 by 0.65 wafer chip scale package with 0.35 mm pitch that provides a 1 microamp of quiescent current. For those who don't need that size, the TBS7805 is also made in a 1x1 quad flat no lead package. This not only makes this device one of the smallest sized LDOs, but also one of the lowest IQ devices on the market, giving you the best of both worlds in terms of size and performance. An enable or shutdown pen is another simple solution if you're designing to conserve battery life. Smartwatches, fitness trackers, phones, and even drones can employ the solution for a battery boost. Drones, out of all the consumer electronics that were mentioned, spend very little time in standby mode because they're usually only idle pre or post flight. However, you can still save battery life by shutting down LDOs attached to those modules not needed for flight. A good example for these modules are the image sensor, as this is only needed when the user wants to record videos or take photos. Since this module is off, the shutdown current is the only drain on the battery, which is even lower than the LDO's quiescent current. Although battery life is highly dependent on the load conditions while running, LDOs with low quiescent current are a simple solution to help boost the runtime of any battery-driven device. These small devices are not just limited to consumer electronics either. They play just as big of a role in industrial applications such as smart meters, building, and factory automation. So even though designers sometimes overlook quiescent current, they can ultimately make the difference in an application running for a few more seconds to days or even years. Now that you've learned the importance of quiescent current, make sure to always account for it in your power dissipation calculations. That's all for today's video. Be sure to check out our online portal at ti.com/LDO for the latest information. Stop by our training and support homepage to watch the latest LDO Basics videos, or head over to our E2E forum and read what our experts have to say about LDOs. We look forward to seeing you in our next LDO Basics videos. Have a great day.